Hello, let's come to fluid tensions and shear stresses, and I have to explain a bit more about this effect. I, I already introduced viscosity to you, and you have to know a lot about viscosity, about Newton fluids and non-Newton fluids to understand this lecture, but I explained this in the lecture 2 week ago. Okay, let's come to fluid tensions and in resting fluids. I already explained you what the pressure is. If we have a force on the fluid, if we have weight of the fluid, we get pressures inside a fluid, and pressure and stresses and tensions are really similar. Yeah? They're more or less the same. And if we have, I told you about viscosity, the effect of viscosity. I explained what it is. Viscosity, if you multiply the viscosity, which is a fluid property, with a gradient, with velocity gradient inside the fluid, you get tensions, you get the stresses inside the fluid. But if we don't have a velocity gradient, if we don't have a movement of the fluid, we probably will get no stresses. So now in this chapter we deal with non-moving fluids, we deal with hydrostatics. So if we have a Newtonian fluid and it is in the rest, there are no shear stresses. Yeah? And normal stresses, okay, they occur depending on the pressure. If we have walls of a vessel, we have a fluid inside, we get normal pressure, we get normal stresses in the walls depending on the weight. And yeah, okay. And one thing is that has to be mentioned also, inside fluids, the friction or the static pressure, if there is no movement, will never depend on any angle. That has something to do with the hydrostatic paradoxon I explained you before. Okay, so let's have a small look at our resting fluid. Yeah. We have here a resting fluid, we have height, we have gravity, we have our fluid element, and now this fluid element has an angle, but because there's no movement of the fluid, no movement of the walls, then we will have no shear stresses. You ask me now, what is movement of the walls? Of course, in fluids we will always have a lot of technical solutions where we have moving walls. For example, if you imagine the screw or the propeller of a ship, yeah, that's a moving wall, and it will act on the fluid and it will cause forces or high forces. Okay, we will come to this circumstance later, but in a static pressure inside a fluid is independent of the direction. Please always remember this. And here again I added you a formula for, but imagine this is only true for Newtonian fluids. What is a Newtonian fluid? I explained it in a former lecture. You should know it. All these laws I teach you now are only true for Newtonian fluids, and all our exercises will only be done for Newtonian fluids. In non-Newtonian fluids, the world is totally different. Yeah? We can have dependency on friction angles. Okay, so we make a short repetition. I already told you about shear stresses in the fluid. I explained it to you. If you know the dynamic viscosity eta and the gradient of the velocity inside a fluid, you can calculate the shear stresses inside the fluid. And then, but of course, if it is static, the gradient is 0, and then you get no value for the shear stresses. Later, we will go more into details with the shear stresses in fluids, different to solids. There can also happen an additional effect, the effect of turbulence or swirl. And this would be the description of this turbulence. It's much more difficult because if you have a lot of turbulence, you have high gradients inside the fluid, you will get high shear stresses, and so there will come an effect that you will get somehow a higher viscosity caused by swirls and turbulences. Yeah? And we call this the turbulent viscosity. But that's too difficult now for our hand calculations. We will come to this effect later. Okay. Now let's have a. Now we're more or less. This lecture is more or less finished. We come to the last topic of this lecture, the topic of aerostatic. I teach you about hydrostatic. Where do we need hydrostatic? If you want to build some houses inside the water or submarines, or if you want to build dam systems with high water, with water ponds inside, then we need to know something about hydrostatics. Or if you want to build a windmill inside the sea, offshore buildings, then we need hydrostatics. But let's also come to the world of aerostatics. You think, aerostatics, we can't build a house in the air, but we also need the principle of aerostatics. For example, if we look at balloons, there's a balloon with a big vessel, it's a big ball filled with air, and now we have a burner here at the bottom. We make the temperature inside this balloon higher and higher, and you've learned in the second chapter of this lecture, if temperature of air gets higher, we get low density, lower density. That's also important fact. If we have a gas and we get higher temperatures, we get lower densities. If we have a liquid and we get higher temperatures, we get, the density does not change so much. Let's explain it like this. If you want to know how the fluid properties change in detail, you have to look at tables. And also this balloon flies because of the Archimedes principle, but it's also something I want to introduce very often to you. If we have a fluid, we have an incompressible medium. So if we get a higher temperature or lower temperature in water, the density will not change so much because the fluid is incompressible. But if you have a gas, like air in this balloon, we have a compressible fluid. We can press it together or we can expand it. And how can we describe this behavior? We can describe it by Boyle-Mariott's law, which is here the ideal gas law. And that's a law that is something you should put on your formula sheet, that is so important. We have a pressure times a volume, and it depends on mass, universal gas constant, and temperature. Universal gas constant is about 8.314 joules per mole and Kelvin, so it describes if you get higher energies, it describes the movement of the molecules, the number of the molecules. It is a constant. When you use this constant, be a bit careful. There are many different descriptions and units of this constant, and you can find wrong constant very easily. Yeah? So always try to use the right units, but it's just a value, and if you have a mass of this balloon, a temperature, we can calculate how the pressure change or the volume change in this balloon will happen. And then you have a density, because volume divided by mass, or let's say mass divided by volume, is the density, and if the density changes, you will get, depending on Archimedes' principle, a rise up of the balloon. Okay, and that's something I always want to mention. We are here in the lecture of fluid dynamics and of hydrostatics, and liquids are our business. Normally, if you have physics or so, you only deal a little bit with some densities and not so detailed. But here in this lecture, you have to look really, really close on which fluid you use, which liquid you use, how it changes over temperature, and how it influences your behavior of the fluid flow. If you have two fluids and they have different viscosity or different density, they behave totally different. If you want to build something for a plant for oil, or a rig for milk or water, the fluids are different, and so your industrial plant should, and your pipe system should look different depending on the different properties, on the different viscosities, different densities. The walls have to have in your plant have to have different thickness. If you have higher density fluid, you have lower density fluid, the wall can be thinner. That's always something you should keep in mind. And I can tell you these fluid properties, every fluid has different properties. This circumstance, it is inside ANSYS CFX. You can find a big library if you want to know detailed information about air or helium or water fluid properties. You can look into ANSYS CFX. There's another good tool called RefProp, where you have big tables of the fluid properties, or I always will give you some such tables, and then if you get tables and exercises, it can always happen that you must make interpolation, so you should know how to do interpolation in tables. And yeah, I can tell you these fluid properties are sometimes really expensive. My time at Bosch company, I had a lot to do with different diesel fluid properties, different densities of diesel fuels, and all over the world diesel is different. Yeah? We have a lot of different diesel types with different viscosities and with different densities and different speed of sounds. And if you want to measure the exact density or the exact viscosity and the behavior over pressure and over temperature, then you have to make measurements of the diesel. And imagine, we use diesel systems around about 2,000–2,500 bar. Yeah? So there were a lot of data to measure for example, for density change or viscosity change over this broad range of pressures and temperatures. And this was really expensive. We paid a lot of money to make these measurements of fluid properties, because they work over years only on these measurements. Okay, so, but let's come back to aerostatics. Yeah, in special cases you have also barotropic fluids, and barotropic fluids are also a bit more complicated. I just give you a formula, don't want to explain too much, but if you look closely on this exponential form, you can imagine it has something to do with the ideal gas law. Again, we have gravity, gas constant, temperature. Here we have height over the ground. Yeah? So it has something to do with this gas law, and it has something to do with the height of the balloon over the ground of the Earth. Yeah, maybe you've heard, if you go into a greater height over the ground, the pressure gets lower and lower and lower. Maybe one question from my side. I told you often about the atmospheric pressure. It is about 1 bar. And do you know why the pressure here on the ground, on the Earth, on our planet is about 1 bar? I can explain it to you. More or less, our atmosphere of air is around about 10 kilometers. Of course, it's much higher, but if we come to outer regions of the atmosphere, the air gets thinner and the density gets thinner. So let's say round about an airplane flies in 10 kilometers high, and let's say round about the height of our atmosphere would be 10 kilometers. Then if we have air, how much is the density of air? That's something also should always remember. How much is the height of water? 1000 kilograms per cubic meter. Air, 1.2244 or 1.2, let's say 1.2 kilograms per cubic meter. And if you sit in the exam, you can't imagine the density of air, then okay, let's say 1 kilogram per cubic meter. So please remember, water has a density of 1000 kilogram per cubic meter. Air has roundabout a density of 1 kilogram per cubic meter. And if we now look back on our planet, we have an atmosphere, height of the atmosphere of round about 10 kilometers, and we multiply this 10 kilometers with the density, we get exactly 1 bar here at the ground. So you see, it's the same principle as in hydrostatics. If you look at aerostatics, we can use the same formulas to calculate the pressure depending on the height of the fluid as if we use them in hydrostatics. Okay, of course this is every scientist will be angry with me with this explanation, but it's just roundabout. Okay, so let's have at last a short look at our learning controls, and I want to close the lecture. So please keep in mind, what should you learn in this lecture? You should know what is the hydrostatic pressure. Always remember hydrostatic pressure, rho density times gravity constant times the height. Okay. How does a hydraulic press work? Yeah, the working principle of a hydraulic press: you have connected vessels with hydraulic fluid inside, maybe oil and water. In most of the cases, of course, oil. And if you have different areas of your piston, then you can generate really high forces from small forces. Okay, let's go back to the slides if you want to have the explanation. You have to be able to explain the hydrostatic paradoxon. What is it? Yeah? Can you save your life if you are a scuba diver and you dive into a cave? I don't think so. Let's have a look at this hydrostatic paradoxon, and you have to be able to explain, is a force on the ground of a vessel with different areas the same, or is it a different force? And can you calculate hydrostatic pressures on inclined surfaces? We will calculate it in the exercise, and keep in mind, if it gets too inclined or too complicated, or round surfaces or any angles or difficult objects, you will probably need under CFX to do it. Yeah, you can't do it ahead. You have to write. If you have complex geometries underwater, you have to divide all the small areas of this object, of this undersea boats or manholes or valves. You have to divide it in small area elements, and then calculate the force on every small element. And this is too tough for us now and too time consuming. It can be millions of small areas that have to be calculated, and therefore we use meshes and numerical discretizations with our tool under CFX. And you already did it. And you have to be able to explain Archimedes' principle.